Welcome to the presentation of the Nisshinbo R5601 analog front-end IC. Nisshinbo Micro Devices
has over 20 years of experience in developing protection ICs for lithium-ion batteries. We started with single-cell protection ICs, mainly for mobile phones, but our portfolio expanded significantly due to the vast popularity of lithium-ion batteries. These batteries can be found in almost any portable device nowadays. Our portfolio now consists of one-cell, two-cell, multi-cell, secondary protection, and with the launch of the new R5601, an analog front-end IC as well. As for all our protection ICs, we tend to focus on specifications like low current consumption, high accuracy monitoring threshold settings, small package technology, and enhanced safety circuits. There is a significant difference between so-called standalone and analog front-end solutions. As for a standalone solution, the protection IC performs all tasks, such as cell monitoring, the decision to interrupt the charge and discharge process, and driving the external dual MOSFET transistors. An analog front-end IC performs cell monitoring only and forwards measurement results to an MCU processor by two analog outputs. The decision to interrupt and follow-up action is all controlled by the MCU software. Especially for large battery packs, it becomes more difficult for engineers to work with internally fixed settings like in standalone solutions. There is no possibility to make changes in the settings, as this is all pre-programmed into the IC. In case any change should be made, a different version of the IC should be ordered, which may have a long lead time. This may add a significant amount of time to the development process. An analog front-end IC is much more flexible. The software can be changed at any time, and even a more sophisticated algorithm can be designed for monitoring and interruption process. This kind of solution saves time to market, which is often very important. The R5601 is made by a high-voltage semiconductor process. Specific terminals can tolerate voltages up to 32 volts. It has three different operating modes, which makes the R5601 flexible to adapt to various operating conditions. In the normal operating mode, it consumes only 36 microampere. Current consumption can be reduced to 6.5 microampere by entering a low power mode. Minimum current consumption is achieved by entering a standby mode. Now the R5601 requires only 2 microamp. A high voltage accuracy cell monitor circuit measures the cell voltage of each cell and forwards the analog results to a V-cell output pin. The cell voltage amplifier has a gain of 0.6. Another high accuracy current monitor circuit measures the battery pack current and forwards analog results to a VIOut output pin. The cell current amplifier has a gain selection option of 10 to 40 or 5 to 10, depending on the selected product version. By register setting, a low or high gain can be selected. A wake-up circuit is embedded to wake up the IC from a low power and standby operating mode. The external MCU requires a power supply as well. Therefore, we have added a voltage regulator into the R5601 to reduce the number of components on the circuit board. A high accuracy reference voltage output is available for use with an external analog to digital converter. A short circuit detection circuit is integrated. In case of any cell voltage imbalance, it can be corrected with the integrated cell balance function. The IC can be controlled by an MCU processor through a two-wire I2C communication interface. The R5601 is embedded in a TSSLP16 package. This slide shows an internal block diagram of the most important circuits. A multiplexer is used to select cells one by one and measure the cell voltage. A cell balance circuit to correct any cell imbalance. The MOSFETs for this purpose are integrated. A logic circuit to control various functions. A short detection circuit monitors for charge and discharge currents beyond normal operation. A cell current monitor circuit, a cell voltage monitor circuit, a reference voltage circuit, an internal voltage regulator. On this slide is shown how the key components such as an additional MCU and the battery cells are connected with the R5601. The VC1 to VC5 pins are used to connect the battery cells. RSN and RSB pins are used for current measurement. The SDA and SCCL pins are used for the two-wire I2C interface. The alt pin provides a flag signal in case of any fault event. The VREF pin provides a reference voltage for the external analog to digital converter. The VIOut pin provides the analog current measurement results. The VCell pin provides the analog voltage measurement results. The VROut pin provides the supply voltage for the MCU processor. Here an overview of functions which can be controlled by the two-wire interface. The operation mode can be controlled to select normal, low power and standby mode. Selection of the cell for voltage measurement. Selection of the cell for the cell balance function. A selection to measure and calculate the cell current can be made. Low or high current monitoring gain can be selected. The low-high combination is selected by the product version. A specific correction value can be set for VCell and VREF. The short circuit threshold can be specified by register. Fault event information can be obtained, such as short circuit, momentary voltage drop, wake-up event, and internal error in the IC. In order to measure the individual cell voltages, select a cell by using an I2C command. The cell voltages are measured one by one. A multiplexer is used to connect the cell terminals to the differential amplifier. An amplifier provides an analog voltage to the VCell output after amplification. The cell current is sensed by an external resistor R-sense. We make use of the voltage drop over the resistor to determine the current level. At first the voltage at the RSB pin is measured, followed by the voltage at the RSN pin. By using the specified formula, it is possible to calculate the current level. The amplifier gain can be specified by the internal register settings. In low power mode, it is possible to reduce current consumption. A number of internal circuits can be disabled in low power mode, such as cell voltage monitoring, current monitoring, external reference voltage, thermal shutdown function, short circuit detection. Only the voltage regulator and wake-up circuits remain operational. The current consumption in this mode is lowered to typically 6.5 microamp. In standby mode, also the voltage regulator is disabled, decreasing the current consumption to a minimum of 2 microamp. Only the wake-up circuit remains operational. To release the low power and standby mode, the voltage at the RSB pin should increase above the internal wake-up threshold voltage. This wake-up threshold voltage can be specified in the register settings of the IC. A selection from 4 levels can be made. Alternatively, one could also pull up the alt pin to resume to normal operation mode.